Might as well. There we go. All righty. Okay, so off we go. So what we're going to do today is we're going to take a look at another type of hypothesis test. But just to remind you, just to make sure that nobody purchases SPSS when you don't need to, SPSS can be accessed for free at home, but you have to go through IU Anywhere in order to get it. So I highly recommend, we haven't had SPSS homework due yet. Number one, highly recommend that you do all your homework as much as you can using SPSS. So for whatever hypothesis tests you need to run, practice running them in SPSS. Use your homework as an opportunity to practice that. And if you have not already installed the IU Anywhere Citrix receiver, if you've not already enabled it, set up the Java requirements, whatever those little intricacies are required for your computer, I highly recommend do that as soon as possible, because there's about a 30% chance that you will need to contact the IUSB IT help desk in order to get that finalized so that it works. So just, don't procrastinate on it. Make sure that it's all working and ready to go for you so that when you need to do this, work from this at home, it's ready, it's working, and it's good to go. All right, so today we're going to talk about spanking. No, we're going to talk about punishment and how it can change behavior. So people used to spank children. They used to use that form of behavioral change for their children. These days, they don't so much. These days, they've changed it to timeout procedures. So instead of getting spanked, children will be placed in timeout where they're basically staring at a wall for maybe a minute. So this has been shown to be a very effective way of changing children's behavior. And we're going to take a look at an interesting experiment that looked at whether or not timeout will change adult behavior. So if you put adults in a corner, if you put baby in a corner, will that actually change their behavior, or will it not be effective for adults? So that's what we're going to look at today, an experiment that tested whether or not timeout will work for adults. And this is going to be our introduction to using the t-test for an experiment with dependent means. So we're going to see how to do that in SPSS, and then we're going to see, I'll just mention the homework assignment that you'll be ready to do, and also we'll have some extra practice with SPSS ready to go. All right, so let's take a look at this demo problem here. So placing children in timeout can be an effective form of punishment. Research suggests that this same technique can also be effective for adults. So this is an actual scientific experiment. You can check it out in Canvas. I've uploaded these files. So in the study, participants were shown a series of colored shapes and had to classify each stimulus into one of two categories. Each correct response was rewarded with a nickel, and each incorrect response was punished by a timeout period of 5 or 10 seconds. So during one block of the experiment, these subjects received 5-second timeouts every time they were wrong. And then during another block of the experiment, the subjects received 10-second timeouts when they were wrong. Those blocks were counterbalanced across subjects. So some of them started with the 10-second and then the 5-second. The other half started with the 5-second and then the 10-second. During these timeouts, during these 5 or 10 seconds, no stimulus was presented and participants had no opportunity to earn more nickels. So they were literally placed in timeout. The dependent variable was the overall level of accuracy during a series of trials. Assume that each participant completed a series of trials using the 5-second timeout period and another series using a 10-second timeout period. Data for a sample of 9 participants are as follows. Does the data indicate a significant difference? We're going to use a two-tailed test with an alpha of 0.05. In this case, the two-tailed test is the appropriate test because you don't know if this timeout procedure is going to improve the accuracy, if these adults are going to say to themselves, well, I'm losing my opportunity to earn more nickels, so I better be more careful, I better increase my accuracy, or will it have the opposite effect? Will these adults get frustrated and say things like, I'm being treated like a child, I can't believe they gave me this timeout, and then they'll get angry and then they'll start making even more mistakes. So will accuracy go up or will it go down? We have no reason to expect either or, so we're going to use the two-tailed test with an alpha of 0.05. All right, so in this situation, though, the key here is that each participant completes both conditions. So participant A here, they scored 71% accuracy in the 5-second timeout condition. Their accuracy went up to 86% in the 10-second timeout condition. Subject B ran in both the 5-second and 10-second timeout condition. And her accuracy was 68% correct in the 5-second timeout condition and 80% correct in the 10-second timeout condition. So each of these subjects ran in both conditions. And that's the key to the dependent means t-test. You have one subject being run, or you have a set of subjects being run in both conditions of an experiment. So in this situation, what we're looking at is now we have an unknown population. So we don't even have a hypothesized population anymore. So how accurate should these subjects be? Who knows, right? 50%, 60%, 70%, 80%? I don't know. So we can't hypothesize a mean. It's not like we know they spend 18 hours doing this and we can cut it in half so that there's no preference. So we have that hypothesized mean. Sorry, we don't have the hypothesized mean. And we want to know after treatment, does this sample change so that it belongs to a treated population? So in this case, we take our sample from the unknown population and we measure it. And then we take the sample from the treated population and we measure it as well. So this is the first time we're doing something that really seems intuitive. And we say, all right, we want to apply this treatment. We want to apply this extra 5 seconds of timeout. So why don't we measure how the subjects are doing in the 5-second timeout condition, and then we'll treat them with the extra timeout, and we'll measure how they're doing in the 10-second timeout condition. So subjects are measured once pre-treatment. Subjects are measured a second time after the treatment. You measure them twice, the dependent means design. So it's so-called dependent means because the scores in the 5-second timeout condition and the scores in the 10-second timeout condition are dependent on the same people. So that's what we mean by a dependent means test. The scores in each condition are dependent upon the same people. That 71 is dependent upon participant A. That 86 is also dependent upon participant A. And the logic behind this is a little bit like a single sample t-test. And that's why they're grouped together in the same chapter. Because in reality, what we do in this statistical test is we figure out the difference between the two conditions. So you can see here that going from 5 seconds to 10 seconds, well, let's do it the opposite. Going from 10 seconds to 5 seconds, decreased accuracy for A by 15%. Going from 10 seconds to 5 seconds, decreased accuracy for B by 12%. Going from 10 seconds to 5 seconds actually increased the accuracy for subject C by 3%. So those are the differences. And in our analysis, we're going to analyze what those differences are and see if it's too big to have occurred by chance. So the logic is that if there is no difference between these two conditions, if people are just as accurate in the 5-second condition as they are in the 10-second condition, then this average difference should be equal to 0. Right? If there's no difference between the 5-second and 10-second condition, then the average difference should be 0. We found an average difference of -7. So is that indicating that there is really a difference? Or did we just get, what do we got there, 9? Did we just get 9 weird people from one side of this accuracy distribution? What are the chances of that occurring? That's what we're going to figure out with our hypothesis test. All right, so it is a dependent means t-test. It's a new t-test. However, it's still a hypothesis test. And what that means is that we have the exact same 5 steps that we're going to go through in order to do this hypothesis test. So let's get that going with step number 1. restate the question as a research hypothesis and a null hypothesis about the population. The question that we want to know, is there a difference in the accuracy between the 5-second and 10-second timeout periods? We can't ask that statistically, so we have to change it into a research hypothesis and a null hypothesis. Recall that it's two-tailed. So the research hypothesis is that there is a difference in accuracy, and we write that as the mean accuracy for the 5-second condition is not the same as the mean accuracy for the 10-second condition. This covers maybe the 5-second condition has higher accuracy. It also covers maybe the 10-second condition has higher accuracy, just so long as they don't equal each other. There is some effect of that change in timeout. The null hypothesis is the complete opposite of the research hypothesis. So the research hypothesis is that there is a difference in accuracy. The null hypothesis is that there is no difference in accuracy, and the 5-second timeout condition accuracy is the same as the 10-second timeout condition accuracy. So that treated sample, that 10-second sample, does not belong to that treated population. It still belongs to that original unknown null hypothesis population. All right, so that's the step one, the research and null hypothesis. Step two, determine the characteristics of the comparison distribution. SPSS is going to do this. So once again, we're going to go through SPSS and figure out where do we look for this information, and let SPSS do the heavy calculations. Step three, set a cutoff sample score or critical value. We are now going to switch this explicitly to setting a cutoff probability. So I'm glad we still got this up here. The reason we can do this is that setting a cutoff score is directly tied into a cutoff probability. So the two of these are linked. That's why we have that table that does not change its numbers. So instead of using a sample cutoff score, where we're going to have to go outside of SPSS, go to our appendix, look up those values, and you will have to do that for your homework. To help us do everything that we need to do just in SPSS, we're going to, instead of setting a cutoff sample score, we're going to set a cutoff probability. So again, we can do this because scores and probability, they're tied together. They're inseparable when you're dealing with these distributions. All right, so your cutoff probability, this is going to be the easiest part of exam number 3. Your cutoff probability is equal to your alpha score. So cutoff probability is equal to alpha. That is given to you in the question. In this case, it is 0.05. So our probability line in the sand is 0.05. Normally, we would take that 0.05, split it into 2, find our 2 cutoff scores. But again, scores and probabilities locked together one-on-one. So instead of that, we're going to shift to looking at probabilities and comparing probabilities, and we have our cutoff probability equal to our alpha, an alpha of 0.05. All right, determine your sample score on the comparison distribution. SPSS will do this. So determine your sample score on the comparison distribution. SPSS will find your score and determine your sample's probability on the comparison distribution. SPSS will find that as well. And that's going to be your p-value. And like I said before, SPSS will do this for you. All right, so now that we know what SPSS will do and what we need to do, let's get this going. So this data can be found that we need in the Excel sheet 22-practice-November 1st, Chapter 8, Introduction to the T-Test. And as before, there are screen grabs of this so that you can follow along instead of trying to take notes. So let me get the Excel sheet open here. So this is what we're looking for. This is the data that we are going to be using. So let's zoom in on that. And there we are. All right, so here we have our 9 subjects. Here we have our 9 scores for the 5-second condition and for the 10-second condition. All right, so we got SPS open. So let's start doing our entry of our data. So the first thing we're going to do is we're going to take that 5-second condition data there. We're going to take the raw scores for the 5-second condition. We're going to copy it, so we can go Control-C, go over to SPSS, and we're going to paste it so that we've transferred those into our SPSS data. Give me 1 second. I want to make sure that we keep this as consistent as possible. Not person. 5. All right, that'll do. Okay, so we transfer in the accuracy from the 5-second condition. And SPSS assigns it a variable name of var00001. Horrible name for humans. We will forget what that is in about 3 seconds. So we're going to go down here to variable view. And we're going to click on that. And I would love to rename this 5 seconds, right? That as a human is what I would love to do. But if I hit enter on that, SPSS is going to get angry at me. And it's going to send me a warning message. And it's going to say, your variable name contains an illegal first character. So SPSS, because it's a throwback program that has been built on top of a 90s programming structure, does not allow us to name our variables using a number. So we're going to have to employ some human ingenuity. So instead of 5 seconds, how about second 5? That works. All right, so we're going to call it second 5, SECOND 5. We're under our 8-character, limit just to be sure. So that's going to work. So we're going to call it second 5. So we have our 5-second data in there. Everybody got that so far? All right. Now we got to copy and paste our 10-second data in there. So we're copying and pasting our 10-second data. We highlight our raw scores. We copy it. We go here. And now the question is, where do we paste this in in SPSS? So where do we... I think they would have a zoom here, but they don't. All right, so where do we paste this here? We basically have 2 options. One of them is right, one of them is wrong. We could paste it underneath here and then have a second row where we indicate which condition our scores were from. So maybe we paste it underneath and we have, that second row there say, all right, this is the 5-second condition, this is the 10-second condition. Or maybe we paste it up here and then we have that second column be, this is the 10-second condition. So we have a decision. Which one of those are we going to do? And the thing that's going to help you the most in formatting your SPSS data is to remember that each subject gets one and only one row. So subject number 1, subject A, that is their row. And any scores from subject A has to go into row number 1. So when we have this score in the 10-second condition from subject A, the only place we're allowed to put that score is in row number 1. And the only place we can put it in row number 1 is if we copy and paste those raw scores into that second column. So in this case, subject A, both of their scores are on row number 1. Subject B, both of their scores on row number 2. Subject E, both of their scores on row number 3. And that's going to help you remember where they're supposed to go in terms of how to format your data. The last thing we got here, we got another horrible variable name, var00002. So we're going to go back to the variable view. We've learned our lesson. We're going to call this second 10. That's good enough to jog our human brains. So now we have our data for the 5-second condition in row number 1. We got our data for this 10-second condition in row number 2. So far, so good? All right. So next we go, and now we have our data formatted. Let's run the actual test. So we go to Analyze. We go to Compare Means. Remember, we were going to stay in Compare Means. And we are doing a dependent means t-test. And I would love it if somewhere here it said dependent means t-test. So it says independent samples t-test, so we know that's clearly out. We're not going to go with that one. But nowhere does it say dependent means t-test. So this is the one instance where SPSS is being a little sneaky, being a little coy in terms of what's the correct test to choose. And the one that we're going to choose is paired samples t-test. So a dependent means t-test is done in SPSS by a paired samples t-test. And again, you have that idea of two scores that go together. So make a note of that. Unlike the single sample t-test, where you have the one sample t-test option just sitting there and the two of them make intuitive sense, for the dependent means t-test, you got to choose this paired samples t-test. All right, so we choose the paired samples t-test. So once again, just in case you were blinking, you go to analyze, you go to compare means, and out of those t-tests, you choose that paired samples t-test. All right, now what do? We need to take our variables here, our raw scores, and we need to transfer them and let SPSS know which one of those is variable 1 and which one of those is variable 2. What SPSS does, if I remember correctly, is it will do your t-test in terms of variable 2 minus variable 1. If that is important to you, and sometimes it is when you're doing one-tailed tests, you want to remember that it typically, I think it does, variable 2 minus variable 1, and you can put in your variables so that you have one in one and the other one in the other one. So we got 5 seconds as the first variable, 10 seconds as the second variable. This is going to do the 10-second accuracy minus the 5-second accuracy. For this example, we really don't care because we're doing a two-tailed test. So either or, we're just looking for a difference, whether it's a positive difference or a negative difference. Sometimes, however, you want to have the direction correct. So if you're asking for, did the scores increase? You want SPSS to analyze it in a way that will lead to a positive difference if there was an increase. Did the scores decrease? You want SPSS to analyze it in a particular way to give you a negative value if it did decrease. So I wish there was an easier way to figure this out. It takes a little bit of mental gymnastics, but if you do it the wrong way, if you set it up the wrong way, that little double arrow right here, this little arrow right here, lets you switch things around. So typically what I do when I'm doing this for real, when I'm doing this as part of the research that I'm analyzing, I'll run it one way, and if I take a look at the output and I say to myself, whoops, I did it the wrong way, I'm just going to pop back to this part, flip those variables, and I'm just going to run it again. So I'm just mentioning that for your homework and for exams. If you want to take away that mental gymnastics, run it in a certain way. If you're finding out that you're getting negatives when you shouldn't be getting negatives, just close that output, go back, switch it up, and run it the opposite way. But importantly, what we need to do is we need to have one of those variables as variable 2, one of those variables as variable 1. So once you have those entered, we hit OK, and we get this output right here. And because we are running close to the edge of our time, I am just going to assume that everybody has those numbers. So just very quickly take a look. Does anybody have numbers that are significantly different from those? It looks good. All right, let's wrap up today's class. T-test with dependent means. Last thing we need to do, step number 5, decide whether to accept or reject the null hypothesis. If that sample t-score is beyond the cutoff t-score, we would accept the research hypothesis and reject the null hypothesis. That has not changed. If the sample t-score is within the cutoff t-score, we would accept the null hypothesis and reject the research hypothesis. That hasn't changed. However, we are now transitioning where instead of cutoff scores, we're going to use probabilities. So the new rules that are equivalent, they're the same idea. If the p-value that we find is less than the alpha, we're going to accept the research hypothesis and reject the null hypothesis. If, on the other hand, that p-value is greater than alpha, we're going to accept the null hypothesis and we're going to reject the research hypothesis. So let's take a look at our table and see what we need to do. So we're going to zoom in there on a bit. And as always, that top row, that top table, that gives you a lot of information that lets you know whether or not you ran and entered your experiment correctly. So for example, the means in Excel, you can calculate those. 76.1% for the 5-second condition, 83.1% for the 10-second condition. You can double check that. Gives you confidence that we entered in that data correctly. SPSS is telling us we got 9 subjects in each condition. That's how many we're supposed to have. Gives us confidence that we ran that correctly. Next thing we need is we need that comparison distribution. We need to know what is the, the mean of the comparison distribution is going to be 0. What is the standard error of the comparison distribution? And what is the degrees of freedom for that comparison distribution? For 3, what is our cutoff probability? And 4, what is our t-statistic? And what is the p-value associated with that? So where do we find that information? Well, we go down there for the standard error for the comparison distribution, standard error of the mean right there. So we have our standard deviation of 2.0 for our comparison distribution. This mean for of 0, this is always going to be the mean for any dependent means t-test you ever run. You will not find this anywhere on SPSS because it never changes. It's always 0 for any dependent mean comparison distribution. So that's why you won't find it anywhere. There's our standard error. Where's our degrees of freedom? Right over there. So we have our comparison distribution, standard deviation of 2, 8 degrees of freedom. For our cutoff probability, that's going to be given to you in the question. It was an alpha of 0.05. Our cutoff probability is 0.05. For your homework, you're going to have to look up your cutoff t statistic using 0.05 and then using the t-distribution table. All right. Step 4. In this case, it had the 5-second condition minus the 10-second condition. SPSS will very nicely tell you which one is subtracted from which other one. So that led to a decrease of 7%, meaning that the 10-second condition is 7% more accurate than the 5-second condition. And if those mental gymnastics are not in the direction you should be doing it, close this down, go back, flip the variables. You'll thank yourself for doing it. The t-statistic, the cutoff t-statistic, minus 3.5 right there. So that's our cutoff t. So if you were doing this the old way, you would compare that t-score to your cutoff t-statistic. However, we are now moving to probabilities. So the p-value is right there. So we have a probability of 0.008. We have an 8 in 1,000 chance of getting a t-statistic that extreme if there was no actual difference between the 5-second and 10-second timeout condition. All right, so if the p-value is less than our alpha, that's our p-value, that's our alpha. 0.008 is less than 0.05. So we're going to accept the research hypothesis, we're going to reject the null hypothesis. If it was the opposite, if we ended up with a p-value higher than our alpha, we would accept the null hypothesis, reject the research hypothesis. As it is, we have that smaller p-value than our alpha, so we reject the research hypothesis, and as it turns out, 10-second timeouts do lead to higher accuracy than the 5-second timeout period. All right, we made it in under the wire. So, as always, keep up with the MyStatLab for the pretest points, especially since you're not using SPSS for your pretests. You can earn those extra points. If you do want to use SPSS for the pre-test, I highly recommend give it a shot learning it on your own. YouTube has tons of information. SPSS tutorials have tons of information as well. But if you can't get it to work, you can earn 100% on those MyStatLab study plans. Extra practice, there's an extra practice PowerPoint that ties into the Excel sheets that were uploaded for today. So highly recommended, give those extra practice a shot. And your homework assignment, this is clearly going to have the new due date put on it. So your homework assignment right now, let me just double check when that is due. I know we're running a little bit over time here, so bear with me for a moment. So for your homework assignment, just want to see when that is due. Right. Okay. So your homework assignment for today is going to be due November 13th. So November 12th by midnight. I'm pushing it to that moment because you have enough information right now to do about half of your homework assignment. You can do the two-tail test. We have one more thing to go over, which is how to do a one-tail test using SPSS. So if you want to start some of your homework, come back to it later, feel free. But just know that we've only covered two-tail tests using SPSS. We got one last thing to do, which is going to be the one-tail test. And that is what we are going to be doing in the special class that is scheduled for tomorrow. So tomorrow, it's a special online-only class. So sometime tomorrow, I'm going to record a lecture to make up for the week that we missed. I'm going to post that to my YouTube channel in the stats playlist. And sometime before, sometime before we have our next class, watch that video, just kind of follow along, keep up to date, and we'll catch up for the week that we missed. All right, thank you for the overtime. That is it for today. And again, I will announce it in Canvas when that when the lecture is available. Please make sure that you watch it before we meet again next Tuesday.